All right, my name is Jonathan Rustick. I'm from Orbital ATK, Space Systems Group, Tech Ops East, and I am the product architecture lead for fault management and system autonomy for the Space Systems Group. And so I'll be talking about our automated test architecture today and how we're trying to integrate that with model-based system engineering. The aspect of model-based system engineering that we're working with right now is SysML, System Modeling Language, which is an extension of UML, which I'm sure everybody here is very familiar with. SysML has some of the same promises as UML and some of the same kind of constraints and inhibits to implementing, which is there's a lot of potential, there's a lot of capability, and there also can be a lot of resistance to deploying it to make full use of it. So as we've been investigating SysML and getting some initial training, we're also looking at targeted areas that we can implement it, and this is one of those areas. The two areas that we're focusing on in our group, fault management and system autonomy, one is shown on the top, which is ConOps development. So identifying the overall concept of operations for the vehicle, identifying specific mission phases, activities, sequences, and doing that in a systematic way, capturing it in a central database, which is, of course, inherent to the SysML approach. The thing I'm talking about today is on the bottom half. So that's the top, that's the front end of the program, is doing those initial definitions. It's very important for fault management and autonomy. On the back end of the program, when you're doing V&V, the definition of tests becomes very important. Have you fully identified all of the test cases and scenarios that really qualify the autonomy in the system, that really convey the confidence that the system will work as it needs to in failure scenarios in flight? And of course, these two items, although they happen at different phases in the program, are or should be very tightly connected. Often what we find in our process is that they are not tightly connected, and one reason is because there aren't systematic methods applied and the data is not captured consistently where everybody can access it for all their purposes. So, and again, as we're rolling out a roadmap in both of these areas, and there's convergence because of the tight connection between defining the types of activities, scenarios, and sequences that need to happen, which eventually will be automated on board in various ways, and then bringing in all of the testing and the right test scenarios to merge with that. So just to provide the context for when I talk about fault management and system autonomy testing, there's been a lot of talk about testing and automated testing, and especially in a group that's software focused, we kind of lose sight of, well, what level of testing are you talking about? Are you talking about just analyzing code? Are you talking about unit testing code, function testing code? I'm talking about testing the integrated software system. So all the aspects of software that are involved to operate the system, from the ground software to the flight software. That's the level that system engineering does all of our testing at. And we're qualifying the behavior of the software that we deliver and responsible for, but in the integrated system, because that's where it has to work, and that's where operators have to interact with it. So this picture kind of gives an idea of the context. So the basic level testing and analysis that I show here in software build tests, that is already done. So we have a large scope of unit level testing and code analysis that's done. That is done from a Jenkins server automatically based on any changes to the code that are identified or on a daily basis. That includes some standalone system level testing that's done as well. So that sort of comes along with every build of the system software that we have. On top of that, when we're actually going to release a particular version of the system software, there's additional testing that's done by GNC and by our CNDH flight software team. So that's more functional level testing, so they're verifying that each of the components of the software is meeting its requirements. So from a CNDH software perspective, when I send a command to the task to do X, does it do X, and then tell me it did X? So that's the functional level testing that's done in a real-time system. Once that's passed, then it's deployed to different components of the program for additional testing, spacecraft level testing, which we're involved in, operational rehearsals, which we're involved in, and then the FMNSA testing, which we own. And that's the level of testing where we have flight-like operational scenarios, we have realistic fault injection, and that's where we actually qualify the software that we're responsible for, and also conduct our acceptance testing, which is making sure that all the logical paths for the fault detection and response software is tested. So that's the aspect of testing that, that I'm talking about today, is this system level flight-like operational testing that our team owns. So we developed a test architecture to do this as automated as possible, and that's shown a little bit in this diagram. So the blue identifies components of the testing that are done in an automatic way. Transitions tend to be manual, but you can see in the middle the actual execution of the test on any of our test platforms. So we have test platforms that range from Symix-based, software-only, PC platforms, to many incantations of hardware in the loop. So we have full-up flat sats where we have all of our engineering development units in place, from sensors to avionics to actuators, and then we have scaled-down versions of those hardware-in-the-loop test platforms. This architecture was designed to run in any of those environments, and there's a structure that we set up for this testing where we define a group of tests, and then those all execute. A summary is generated, data is logged, all that is emailed out. We also have an automated data processing tool set that then takes the result of that, evaluates it, narrows in information of interest for test conductors to go and look at, and then we have automated components that generate reports for us. So that's the test architecture that's in place, and this next slide just shows another picture of some of the key aspects of it. So when we have automated testing, what we've done is we've defined a set of global parameters that fully define what a test is. This was set up for our Cygnus vehicle, which is our commercial resupply vehicle for the space station. It's a safety critical system, 2-fault tolerant. So the test architecture was set up to handle 2 actions as a baseline to accommodate up to 2 failures that we have to be protected against. So the set of globals defines the scenario that's going to run. It defines 2 actions. Within each of those actions, there's a set of standard variables that can be selected, the type of action or failure that's going to be selected, the fault isolation zone in which that's going to be injected, so the level of redundancy that it's going to be impacted, the actual fault that's going to be injected, and then we also define the vehicle level response and the system level response that are expected for that failure. So those are all parameterized, and the scripts accept that list of parameters, and they know how to set up a test and execute it and evaluate it real time and post-test. So for the data analysis, we have a tool set that's set up, that's MATLAB based, that's monitoring for the completion of each of these tests. So as the test completes, this tool set sees the data that's generated and says this test is now completed. It then brings all that data over to another location, and it processes all of that data. It does what we call level 0, level 1 analysis to determine, did the expected response in the autonomy in the software execute? Did anything else execute? And then it provides a summary of all that information for the test conductors to go and look at. We also have a tool that will take the results of that with any edits that test conductors need to make and generate a report, which is used to close out requirements. So that's the architecture that we've developed and that we're working with. But a key is still, did you define the right tests, right? Did you pick all the right scenarios to inject the right failures or the right actions to provide a full confidence that the autonomy in the system is going to behave in a way that meets your top level requirements, right? When you have a requirement that says that no 2 failures shall cause a catastrophic event, well, it's very vague, it's very general, right? You can't test every single combination of failures in every single scenario and every single state transition in a real-time system. So we have a lot of analysis that supports it, but we also have testing, and the question again is, have you defined all the right tests? Our safety group will provide us some specific scenarios. They'll say, for a control, we want to make sure that you've tested this specific failure or these specific failures in this specific scenario. So those are fairly easy to hit, but that doesn't provide the full scope of qualification that's needed. So there is a methodology that we follow to go in and define what those are, but it can be difficult to convey that external to our group. So as designers, we understand, right? Everybody, when you design tests for what you've written, you believe that it's acceptable, that it's appropriate, but being able to convey that to somebody so it can be reviewed externally and approved externally can be difficult. So I can provide, if I go back to, I can provide lists of parameters for all of my tests to an external reviewer, but that's not going to necessarily make sense to them, right? They may not understand the terminology that's used in those definitions. They may not understand the scenario that's being described or the expected response. So this is still an issue for fault management in general, and it's an area that we thought might be a good opportunity for us to apply SysML to assist us in defining these tests and conveying what the tests are for external review. So to do that, we set up a series of steps, so sort of a roadmap of, okay, this is low-hanging fruit, but there's still a series of steps that we have to go through to generate something that's useful. The first is obviously just taking what we have and saying, can we implement something in SysML that just pushes out data that drops right into this test set without any modification? And then backing up from that, can we implement something that allows you to define what those tests are? Can we implement something that allows you to visualize what those tests are, all the way back up to the full scope of what SysML is able to provide? So the first step was just defining structure in a SysML context. Right now, for this demonstration, we're using a tool called Magic Draw, which people are probably familiar with. It's used for UML as well as other drawing and model-based concepts. So there's a couple of structural concepts that we looked at for how to define what a test is. And this information, when you define, a test and you have either parts of that test or properties that define the test, it's pretty easy to take that information and drop it directly into a table format that can be used by our tool set. So that's fairly straightforward. The issue here is just what level of structural definition do you want? And so because we have two actions, we have settled on a structure that has a metadata structure with action structures underneath it that fits nicely into how we've defined the test for this particular scope. And again, it generates tabular structures pretty easily, and scripts can take that data and generate our global definition scripts pretty directly. The next step is, okay, well, how do I provide input to those test definitions, right? I can take all the definitions I have and put them into SysML and generate the same data, but that doesn't necessarily help me a whole lot. So then we start looking at how do we define the scenarios, actual test scenarios, to convey what we're doing. So there's a set of behavioral diagrams in SysML, which again, most people are probably familiar with. An activity diagram is shown here on the left. Pictorially, that conveys a lot of useful information to a reviewer or a test conductor to understand based on what is supposed to be happening in this scenario. And then I pick a location in there and say, but I'm going to inject a failure at a particular step or during a particular activity. So that provides some insight into what the test is going to be dealing with. Of course, state diagrams are useful in terms of conveying what the expected response of the vehicle is or what the expected response of the system is. But you sort of need both of these diagrams to really convey the totality of information for a test conductor. And of course, sequence diagrams, which UML users will be very familiar with, provide a lot of detailed context. These type of diagrams are nice in the sense that for at least a single flow with some optional steps in the process, if you so choose to put them, they capture a lot of detailed information, but system engineers hate these kind of diagrams because you have to be very patient to walk through it to actually extract this information again for understanding. So we're working with some of the diagrams that are available in SysML. We're finding that there still is sort of a gap in terms of what system engineers would like to see as a representation of what the system autonomy and software is doing. So there's been a lot of work in developing these for SysML, and they are very useful. But in each one of them, we find that there's information that's missing. In activity diagrams, there's not a lot of paths for optional flows without over-cluttering the diagram. There's not a lot of ways inherently to convey transitions in the type of autonomy that's available at a given step. For a mission like Space Station Resupply or any sort of docking or berthing mission where autonomy will transition based on the distance as you approach different levels of keep-out zones, that is an important aspect of the autonomy that you'd like to be able to convey. You can convey that with state machines and sequence diagrams, but it tends to get lost in the details of some of these diagrams. The other thing that comes that is identified as we start looking at how to define what the test scenarios are that you have, or options that you can choose from for a test, is that, and I've found this each time we've applied SysML, I've kind of had this finding, which is as we look at how to capture that information in SysML and in this model, we see that we haven't really been applying good systematic methodology in defining activities and sequences and concepts of operations, right? They sort of come from a collection and stream of consciousness from different people. And when we try to put them into the SysML context, which forces you into a standard fixed format, we realize that, well, we haven't really been consistent in how we're defining these, and we haven't really been thinking about the kind of information that they really should convey. So that, of course, has been useful and helps to provide feedback into how we define those sorts of activities. And so we've been working on how do I say this is a test scenario and be able to pick a point in here to say, and I want to test at this point, I want to test at this point, and then generate that test structure that was seen in the other diagrams. Another step that we've really just started is how do you identify the failures or the actions that you want to test? We did define a methodology for this for a static analysis that was done for CRS. We had to verify our fault tolerance on approach, basically the ability for the system to identify that it was no longer fail-safe and therefore needed to abort, needed to go away from the space station, because if the right kind of failure happened at that point, we would no longer be safe. So this is a standard requirement from NASA. And so we developed a methodology to identify all of the credible combinations of failures that our system could be exposed to. And we developed a way to extract from our autonomy a model of it that would say, if this certain failure happened, then the system will respond in this way. If another failure happened, the system will respond in this way. And then we were able to model the algorithm that's on board that is looking for non-fail-safe conditions. So we have a methodology for doing this in a static way, and we feel that we can port this into the SysML pretty easily just because of how we captured this data. So we came up with how do we define fault categories under which we're confident every failure will basically roll up into, and how do we then model the response of the system in that case. So we're working on this next as a how do we provide in SysML the list of available failures and faults that the system could be exposed to, so that a test conductor can select them, and then that can be conveyed to test reviewers. So I think I've kind of talked through the bullets on this page of what we've been working towards and what we have found so far. There's certainly a lot of benefit. I still feel that this is a good path for us, that SysML is going to allow us to identify the test scenarios that we want at the level of testing that I do, and then convey that for review much easier than tables or manually creating a bunch of PowerPoint slides. And of course, this really is an iterative cycle. When you enter, and I imagine the same as with UML, when you enter into SysML, you really have to start with baby steps and see, okay, what can be provided, and then you realize, oh, but to do this correctly, I need another aspect in the model to provide data, and you go back and figure out how to implement that, and you sort of build up your capabilities. And so we're still at the beginning of that cycle. And ideally, where it leads to is that we'll be able to automatically generate test cases, right? Once I've provided all of this data into the model, we already have algorithms that can identify credible combinations of failures, so we can then apply that to SysML and basically create automated sets of tests and visualize those with the types of activity diagrams that we showed earlier, and then we can down select those as needed to execute in our test architecture. And future from this, of course, may be of less interest to some of the software engineers in the group, but to a lot of interest to system engineers, is the fact that developing these more systematic methods of capturing the ConOps development, the sequences, activities, and phases, isn't just useful for autonomy development and testing. There are a lot of other system uses of that data. Right now, that data is captured in various documents and PowerPoints, and what you can find is, somebody doing power analysis and somebody doing GNC analysis might be interpreting the valid mission phases, activities, and scenarios differently. So we definitely see a lot of benefit, not just within our group, of being able to define these more methodically. Okay, any questions?
Yay! No, I'm from aerospace, and I find this just fascinating. Actually, I'll wait before we get questions, but just the notion of having the list of credible failures that have been vetted is such a huge deal. Anyway, good for you. Any questions?
That one over here.
Here you go.
So you talked about sequence diagrams, and I'm wondering, is that a document that you're generating, or does the model generate the sequence diagrams?
So right now, we are generating the sequence diagrams. Where we want to go is have the model generate them for us, because what we'd like to do is say, well, first, one of the steps is a test conductor can say, this is the scenario that I would like to test, and have it actually generate the diagrams that describe it so that it can be vetted more appropriately. The step beyond that is then to automatically generate those test sets.
All right, so in your model, is it just the test vectors that you're putting in the model, or is it the actual system behaviors that are going into the model?
Well, it's both. So first, I think what you're describing is a test vector, because we already have a fully defined system, we already have fully defined behavior, we have a fully defined option of what you can test. So we just say, here's the specification. And the next step is, okay, but if I really wanted to select a scenario and what the vehicle would do in that scenario, I need a model of the behavior.
Mm-hmm.
So we need to get to the point where we have that implemented. So that's on the roadmap.
All right, good, thank you. Other questions? Yes.
I just had a question. You were talking about, like, you're using it, I guess, in your program. So how difficult is it to implement across other programs where people are testing and within the company?
Yeah. So since I'm the product architecture lead who's supposed to be enforcing, has been talked about by some of the other companies, more consistency, it's becoming easier to deploy that same architecture on different programs. Any program that uses the in-house ground system, which this is based on, can Maestro can use this architecture directly. So another program that I'm the lead on right now, our mission extension vehicle, which people may have heard about, our Geo MEV program, will definitely be using this. And other programs will more and more. But a lot of what we're trying to get out of it right now is establishing sort of the guidelines. If you were to use SysML and an automated test architecture, here's what it should look like. And if our ground system, changes, because of course, merging with ATK, we have a lot of merging that's going on, right? If we transition to one of our other ground system tools, well, we can re-implement it as long as it has the same features, and that's one of the requirements of moving to those tools. So.
Very good. Other questions? Thank you.
Great.